Hi there. We are finally into chapter 12. Only one more chapter to go, guys. Hang in there. So, chapter 12 is all about correlation and regression. So, let's talk about correlation overall. The beginning of the course, you were introduced to correlation as one of the research designs, but there is actually an analysis related to correlation as well. But when we think of correlation research, all we're thinking about is measuring a relationship between two variables. So it can't state cause and effect. It doesn't talk about differences. So all of our t-tests and the ANOVA looked at the differences between conditions. So it's tests that look for differences. Correlation looks for the relationship between two variables. So there'll be some questions related to like why would we use Pearson correlation rather than t-tests or ANOVA. It's because we're looking for a relationship between two variables, whereas the t-test and ANOVA look for differences between conditions. And specifically, the two variables that we're going to be looking at using Pearson R correlation is measuring two variables that are on a continuous measurement scale or a quantitative measurement scale. So it's very important that those variables are on our quantitative data. So when we get correlation research and we start looking at the relationships, we're looking at number one, the strength of the relationship. How strong is the relationship between the two variables, but also the direction of the relationship. So there could be a positive sign or a negative sign when we're dealing with correlation research. A positive sign meaning there's a positive relationship, meaning as one variable goes up, the other variable goes up. Or there could be a negative sign, and that means there's an inverse relationship, meaning that as the one variable goes up, the other variable goes down. These relationships are often shown with a scatter plot. So, like with t-tests and ANOVA, you're looking at mean differences. Those are often using bar graphs to look at the differences between means. With correlation research, we look at scatter plots. So here's kind of what that would look like. So this first graph you can see is what we would call a positive relationship. So we have temperature in degrees and amount of beer sold. So as the temperature goes up, you can see that beer goes up. And specifically with the correlation, it kind of goes along a straight line, and we'll talk a little bit more about that. But basically, these data points are, so this person in 30-degree weather, you know, uh, 11 beers were sold, for this data point. For this one, 20 degrees, believe it or not, like maybe 12 beers were sold. So it's just showing that it's not a perfect, but it is a relationship that is going along a straight line. Whereas in the other graph, the negative, now we're looking at temperature in degrees and amount of coffee sold. And this is hot coffee. So think of it in the traditional sense of hot coffee. So as you can see, as the temperature goes up, hot coffee sales goes down. So it's talking about a negative correlation or an inverse correlation where as one variable goes up, the other variable goes down. And so there's an X variable and a Y variable. And the X variable is usually kind of that predictor variable. It predicts what's going to happen with the Y variable to some degree. So let's look at kind of the strengths of correlations. And so that's where we kind of come into this. It's linear correlation. When we're using Pearson R, the correlation research must be linear, meaning that on average, the data goes in a straight line. So if you were to look at like research in the past, a long time ago was done on like marital satisfaction over the years, and people had, different predictions. So here's our like x-axis, y-axis. Some people thought that it would go up as years go up. So here's 0 satisfaction and 0 years of marriage. You know, we're at the end of this is like 20 years together, and maybe this is like you know, a satisfaction of 100, let's just say the highest satisfaction you can have. So is what researchers actually found is it didn't go up, but it also some people predicted, oh, as you know, you're married, the satisfaction will go down. But in reality, they found that that relationship kind of went like this. Is its highest, you know, honeymoon, it's the highest, then it goes down. But then as you're together, it goes up, and probably goes up higher than that. I'm sorry, I'm really not that much of a pessimist, but it goes up higher. That never goes quite as high as it did in the beginning. But that's not a straight line. So this would not be, we would not use a Pearson R correlation for this. So specifically, we're going to look at linear relationships that go along a straight line, which is using Pearson R correlation. So as you can see, this is a perfect inverse relationship. So if we look at that, that would be our correlation coefficient would be -1. And the correlation coefficient is what we call our obtained test statistic, the correlation coefficient. So -1 is a perfect relationship, an absolutely perfect relationship. You can't get higher than 1 or lower than -1. So that's a perfect relationship. And as you can see, all the data points fall exactly on that line, on the straight line. The second one is no correlation. There's no real consistent pattern in that data in this second one, they're all over the place. So no pattern, there is no relationship. In this one, this is a pretty strong relationship, a positive 0.90. As the data goes up, or as the X variable goes up, the Y variable goes up. And these data points are clustered pretty closely around what would be a straight line. So the correlation coefficient is positive 0.90. In D, this last one, if you look, this is a negative 0.40. So you can see there's a pattern where the data is decreasing as X decreases, Y decreases, but these are scattered much wider across that linear line. And so that's really what it's measuring is the average distance. These are from that line of best fit, that straight line that goes through the data. It really talks about the distance, and the closer your absolute value is to 1, the closer it is to a perfect relationship, whether it's -1 or +1, just that absolute value of 1 is suggestive of a perfect relationship. So let's kind of look at what I was talking about, that correlation coefficient. So with the Pearson correlation, as you can see, it's notated as a lowercase r. And R is the obtained test statistic. And so, all right, I had to get the book so we can have the chart. So that Pearson R, or the correlation coefficient, is a measure of the strength and direction of that linear relationship between two variables. The perfect linear relationship is either R +1 or R -1. You can have any number in between there, but as it gets closer to 1, it's a stronger relationship. As it's closer to 0, it's a weaker relationship, with 0 being no relationship. So with every change in X, there is a corresponding change in Y, and that's what the correlation coefficient measures. So when you hear the term correlation coefficient, really is what that means is your R obtained. But it is a known value that people can all automatically kind of tell. If you have like an R of positive 0.75, that's a pretty strong positive relationship. But if you have an R of -0.2, that's a weak negative relationship. So it just depends on you know, how close it is to 1 or how close it is to 0. Okay, so here's how we calculate our Pearson R correlation coefficient. At this point in the course, you've done sums of squares in many, many different ways. And that's really what's happening with the Pearson R correlation is you're doing sums of squares. It's just sums of squares in different, used in different manners. The newest one that you're going to use is this SSXY. And the sums of square, SSXY is the sums of square of the product of the variables. So basically, you take your X variable, times it by the Y variable, and then you add those up. And then now in the numerator here, right here, it's just you add up your X values, you add up your Y values, and you multiply them. And then this is the number of pairs, basically, the number of XYs is what you have. Because for every participant, you have a measure for the X variable and you have a measure of the Y variable. A very common things that we look at, like we've looked at, um, social media use related to self-esteem, like the number of hours that you use social media and your self-esteem score. So for every person, they have a social media score and a self-esteem score. So it's the sample size is the number of pairs or the number of XY values or the number of participants, because but they're just not at two different points in time. They're at one point in time. So then we have in the denominator, so the R obtained is the sums of square of the product, and then the sums of square for the X variables times the sums of square of the Y variables and the square root of that product. So we're going to kind of look at how that works. The one thing about Pearson R correlation or any correlation analysis is you can only state the relationship. You cannot state cause and effect. I cannot emphasize that enough. It's not about cause and effect. It's about whether there's a relationship or not, what that strength of the relationship is, and whether it's an inverse or a positive relationship. That's all we can say. We cannot state any cause of an effect because there is research out there that says things like there's a relationship between violent media and aggression in children. So the exposure to violent media and aggression levels. There is a lot of research out there that supports that. But you've probably heard things like violent media or violent video games causes aggression in children. Well, the problem with that is they can't say that because we don't have control of those variables. We don't have control. We don't have a true independent variable. We don't have control of all the factors that could be causing the aggression. So all we could say is there is a relationship. And we have research that shows, yes, there is a relationship, but we can't say that violent video games causes aggression, but we know that there is a relationship that as the use of violent video games increases, the aggression levels increases. There is support for that, but it's not a cause and effect. There's just a relationship between the two. So let's kind of look at an example scenario. So this is a pretty rudimentary scenario. We have, and usually when you get this kind of stuff, this student A, B, C, D, that's usually not there, but I'm doing that just so you can see for every person, they have two scores. So for student A, they studied for 40 hours and their GPA is 3.75. So this is looking at the relationship between hours of study and GPA. So if we were to look at this in a non-directional manner, we could look at like our alternative hypothesis. And our alternative hypothesis would be GPA is significantly related to number of hours a student studies per week. Maybe we have a direction that we're looking for, and we have a prediction that GPA is positively related to a number of hours a student studies per week, meaning that as the hours of study goes up, the GPA goes up, which there's a ton of support for that. There's a ton of research behind that. I'm sure that you could have guessed that. So there's an example of that. So our second kind of step of hypothesis testing. So the first step was stating those hypotheses. The second step is setting the criteria. It's going to look a little bit different. So if, in this case, we're going to use alpha of 0.05. Our degrees of freedom is going to be n minus 2, lowercase n minus 2. Because these variables are two separate variables, they're not the same. One is GPA and one is hours of study. This minus 2 accounts for that there's two separate means. There's a mean for the hours of study and there's a mean for GPA. They are independent of one another. So it's how many participants there was minus 2. So in this case, there's 7 people that we got 2 scores from each. So we have 7 minus 2. Our degrees of freedom for this is 5. And then we're going to look at the back of the textbook. So after in your appendix, after your studentized range statistic, if you remember table, there was the F distribution table for ANOVA, and then you had the studentized range statistic table was after that, was specifically for like post hoc tests. Then in table A.5 is the Pearson R correlation table. So this entire table, and it's 2 pages, it is dedicated to Pearson R correlation. So if we're going to use a two-tell test, a 0.05 two-tell, you're going to look specifically in that area where it says level of significance for two-telled. So you have at the very top level of significance for one-tell, and then it gives the alpha levels, and then level of significance for two-tell test. You're going to use the 0.05 under that. So it's under 0.05, and then you're going to look at your degrees of freedom sub for 5, go down to 5, and then 2 columns over is the 0.05 significance for two-tell test. You should be getting 0.754, and that's two-telled, so it's positive and negative. So that's our criteria, setting our criteria. So let's look at some of the basic calculations that we're going to need just to conduct our Pearson R. So we will need our sum of x, so just adding up the raw scores for the x value. We're going to need to square each of those scores and then add those up. So 40 squared equals 1600, 30 squared equals 900, et cetera, et cetera, so that we can get our sum of x squared. We also need, so that's basically our x variable over here, and then here's our y variable over here, right here. Sorry, I cut through that. But you're going to have to do your sum of y. So adding up the y values. Then you have to square each of those y values. So 3.75 squared is 14.06. 3 squared is 9. 3.25 squared is 10.56, etc. So that sum of y squared is 54.75. Now, to get this sum of xy, that's the new one, you're going to take your x variable, so 40, and times it by its y variable. So 40 times 3.75 equals 150. Then you have 30 times 3 equals 90, et cetera, et cetera. 35 times 3.25 equals 113.75. So you do that for each one of these x variables multiplied to the y variable to get each xy, the product of x and y. Once you get the product of each x and y value, you add those up, and that gives you your sum of the product of xy, 491.25. Once you have all of those, you can start calculating your Pearson R obtained test statistic. It's as simple as that. So here's kind of what that looks like. Here's that bottom row that we just had. I have all of those basic calculations for you. So here is our R obtained overall equation. So let's work on that sums of squared x, y, or sums of square product. So here's what that looks like. The sum of the product of x, y, the sum of x, the sum of y divided by n. And so the sum of x times the sum of y. So this looks like right here, the 491.25, that's this value. Goes right here or here, basically, right? Then you have your sum of x. So that's this value goes here. The sum of y, this value goes here. As you can see, 160, 19, and then your sample size is 7. Once you calculate that, this should be up down here, you get 56.96, and you could plug that in. So that goes right into that numerator. Then you just need to do the sums of square for your x variable and the sums of square of the y variable. So as you can see, here's your sums of square x. You have 4,700 is your sum of x squared. 160 is your sum of x and the sample size. So sums of square x is 1042.86. It goes right here. Okay. Then you're going to do, oops, that didn't stay. Okay. So then you're going to do your sums of square y. Sums of square y is just using that y variable. So 54.75 is your sum of y squared. Then you have your 19 squared. So that sum of y is squared. Remember to square that. Divided by 7, you get 3.18. That goes right here. The biggest mistake I see students make is multiplying these sums of squares together and then dividing the numerator by that and forgetting to take the square root. Now, R obtained, your test statistic, cannot be larger than 1 or smaller than -1. So you need to make sure, is your R somewhere between -1 and +1? If it is, you probably did that right. If it isn't, you probably forgot to take the square root of that denominator. So our R in this case is 0.99. That's an extremely strong positive relationship, almost a perfect positive relationship. So that negative 0.99 is called the correlation coefficient. But now we need to calculate the effect size. And the effect size is called the coefficient of determination. I know they have similar names, but there is a difference. The coefficient of determination is basically the same thing as eta squared in previous. It's the proportion of variability in one variable that can be determined by the relationship in the other variable. And it's basically the variability in the y variable that's determined by the x variable. And all it is you take that R obtained, that correlation coefficient, the test statistic, and you square it. Simple as that. So 0.99 squared is 0.98. So basically 98% of the variability in GPA can be accounted for by the number of hours of study. Simple as that. It's easy peasy. So here's what that APA result is going to look like. So Pearson correlation showed a significant, strong positive relationship between GPA and the number of hours a student studies per week. So you need to tell me, is there a relationship? If there is a relationship, is it a positive or a negative relationship? And I'd be okay if you just said a significant positive relationship. Then you'd have your R. This is your degrees of freedom that you use. That 5 is the degrees of freedom. Your test statistic. This is something that I noticed on the last exam is a lot of people were putting their critical values there. This should be your R obtained. R obtained. Always the R obtained, not your critical value. So make sure you're doing that. Then the next is how P is related to alpha. So P is less than 0.05 because it's significant. If it was not significant, it'd be P is greater than 0.05. Then you tell me whether it's 1-tel or 2-tel. In this case, it was a 2-tel test. And then the last thing you report is your effect size. R squared equals 0.98. That's that correlation coefficient. Or the coefficient of determination, sorry. The coefficient of determination is that 0.98. Simple as that. That's how we calculate Pearson R correlation. So some of the things that we need to remember, correlation is not causation. If we have a restricted range, and let me move my face. Ooh, let's go back. Let me move I'm going to put myself down here now. If we have a restricted range of data, it's going to change the results. So if you look up here, full data, and the range for this data is widespread. So you have scores that are like from 3 all the way to 8. You can see this is a pretty strong positive correlation in this one right here. But if you were only to get a glimpse of people where you just are looking at this small range here, you only have people that scored, from 5 to 7 instead of, from 8 or from 3 to 7, basically. It narrows it down and then it doesn't show, it shows a weak positive correlation. So a restricted range can definitely impact that. And outliers can extremely impact things. So if you look at this top left one, there's this outlier out here. It's just one lonely score all by itself. And is what it suggests is this positive relationship, a weak positive relationship, but it throws off the data is what it does. Over here, if you look, if that one data point is removed, it's actually a negative relationship and it's negative 0.31. So it's still a weak relationship, but it's much stronger than 0.19 and it's a negative relationship instead of a positive relationship. So these are things that you sometimes need to address when you're dealing with correlation research, is if you have an outlier, sometimes you might have to trim your data so that you don't have outliers. Another thing that we need to be aware of is our assumptions to make sure that we have valid results. So assumptions, again, it's more like in the design aspect of things. We want to make sure that we meet those assumptions so that our results are really what they're supposed to be, that they're valid, that if you get a significant result, it's because there is a significant relationship, not because there's some assumption that wasn't met, or even on the other end of the spectrum, you didn't get significance because you didn't meet the assumptions. So for Pearson R correlation, a very important one is linearity. The pattern of data must form a strong line. So this right here is the violation of normality. That is like that research scenario I provided you earlier, where it's years married and marital satisfaction. It would look kind of like that U shape is what it would look like. Homoscedasticity is another assumption. Basically, the variance is consistent among the data points. So as you can see here, the variance, these vary at like the same distance approximately for quite a while. And then all of a sudden, you get this big variance jump over here. That would be probably a breaking of the assumption for homoscedasticity, and that could definitely impact your output or the results of your data and the validity of your results. And then normality is another one. So basically, with Pearson R correlation, you need to have normality for your X variable. You need to have normality of your Y variable, but you also need to have normality of the covariability between X and Y. And there's actually tests within SPSS or PSPP, which is that statistical software that we use to test the hypotheses using statistics, that will test that for you. But one way you can assure is to have sample sizes of larger than 30, as well as making sure that you are sampling from a normal population distribution, which sometimes isn't always assured, unfortunately. So let's talk about when we are using correlation. Sometimes we will use correlation for prediction. Now, when you're doing research analyses in this class, I'm only asking you to tell me to use it for hypothesis testing. I would not have you necessarily when you do a hypothesis test, you do not include regression. I might on the final exam or on some activity or lab, I might ask you to provide me the regression equation and then answer some questions related to that. But that would not be, it would be separate, a separate component from the actual hypothesis test. But correlation can be used for prediction. And when we use it for prediction, we use what is called regression. And that's a statistical method to find that line of best fit, and which is this regression line. And once we find that regression line, then we can start using it for prediction. So to get that regression line, this is the line of best fit, or what we call the regression equation or regression line. And you've probably seen this before. B, which is the slope, times x plus a, which is our constant, is really that predicted, and is what we're doing is we're predicting y using x. So that little hat on y is basically saying this is a predicted criterion, because y is considered the criterion variable, x is considered the predictor variable. So b is that slope. To get b, you're going to take your sums of square xy and divide the sums of square x by the sums of square x. You don't need to worry about this unless you're using PSPP or SPSS. This is what you would use, the standard deviation of y divided by the standard deviation of x times the R obtained. That's if you were using that statistical software. But when you're hand calculating, you use your sums of squares. You don't have sums of squares when you have that statistical software. So first thing you do is calculate your slope, which is that b. Once you get your slope, you can plug that in and to the y-intercept and get your constant, which is that a. And that you would use the mean of y minus the slope times the mean of x. So let's take a look at what this looks